Now let's consider hollow cathode lamp HCl. Okay? This lamp is used for atomic absorption spectroscopy. Okay? Um, Let me give you how the measurement is done. Okay? So you need the hollow cathode lamp for the element you want to measure uh, the the spectrum. For example, if you want to measure the copper atom, the absorption, and then you need copper hollow cathode lamp. Why? Because the copper hollow cathode lamp generates, um, the light whose wavelength is exact the same as the copper atoms. Okay, and that's why you need the many hollow crystal lamp, as many these lamps as the element you want to uh, take a measurement. Okay, um, why? Because the monochromator, how good, no matter how good the monochromator is, it is not possible to differentiate or separate the lines uh, whose um, the what the line width is 10 to minus 3 to 10 to minus 2 nanometers. Yeah? Because there is the resolution limit of a monochromator. Okay, but you need much higher resolution for the atomic absorption or atomic emission spectroscopy. Okay, so you need hollow crystal lamp yeah, whose element is the same as the element you want to analyze. Okay, and this is structure of hollow cathode lamp, right? It has two electrodes. This one, this is cathode. This is called hollow cathode. Yeah? This hollow cathode is made of the elements of your interest. Okay, and then you apply about 500 volts between cathode and anode. And this is anode, and here is the insulating disc, and here this is quartz or glass window. So inside this lamp you fill with neon or argon gas whose pressure is 130 to 700 pascal. Okay, and 500 volts is applied. Gas is ionized. Okay, and positive ion is accelerated and it hits the cathode. Okay, here inside here, uh, you know, this one, the argon gas is ionized, and ions now ions is takes a positive charge, so it is drawn to the cathode. It hit cathode, and high energy electrons beam is generated. This high electron is collided with gaseous atom, and photon emission takes place. All right, and then it is absorbed by analyte in flame or furnace. Okay, which is atomic absorption, not emission. For emission experiment, you don't need these hollow cathode lamps. Okay, atoms in hollow cathode lamps are cooler than atoms in flame, so uh, the emission line of lamp is narrower than the absorption bandwidth of atom in flame. Okay, although the maximum absorption wavelength is the same, the line width is different. Okay, the hollow cathode lamp line width is much narrower than the absorption band. Okay, so as I said, for each element you need the hollow cathode lamps. Okay, and so you can detect only one element with this hollow cathode lamp. Okay, but much better technique has been developed. Okay, with ICP here, multi-element detection is possible. Okay? because in ICP usually ICP emission is detected, so you don't need any lamp for ICP instrument. Okay, and very amazingly, the 70 elements are uh, measurable at the same time. Okay, it is really amazing. And uh, more amazing thing is that with charge injection device, okay, two-dimensional display is possible. Okay, the principle of a CID is very similar to charge coupled device. Okay, I will no, explain in more detail. Okay, this is what I explained, and then this is the line width of the bandwidth of a hollow cathode emission. Yeah, this one is much narrower than this what absorption band. Okay, so that's why this the radiation from this hollow cathode lamp is what absorbed by the atoms of the same element. Okay, yeah. And here to calculate monochromator bandwidth is much larger, so monochromator this cannot differentiate. They're very the closely what spaced this absorption band. Okay. Yeah. Okay, now let's consider the multi-element detection with charge the inductively coupled plasma. Okay, this technique ICP is very powerful technique for detecting elements. But now we can detect many elements simultaneously. How? Look at this figure. This is from charge plate, color plate 24 of your textbook. Okay? Here, the emission line from ICP instrument now comes from this side and it enters through this one, and this is polychromator, and then now it hits this grating. Yeah, and then in this grating, depending on the wavelengths, you see, let's assume you have a sample and it contains many elements. Okay, and each element in ICP the plasma emits its own emission line. Okay, its own emission line, and then those emission wavelengths are all different. So in this grating, they are all diffracted with different angles. Okay. Yeah, you see here, and then at here at this place here you place photo multiplier tubes. Okay, along this frame. Yeah, so each photo multiplier tube detects a specific wavelength which correspond to a specific element. Okay, now there are how many photo multiplier tubes? 1 2 3 4 5 6 or maybe more than 10. The photo multiplier tubes are here, but since each element emits is a specific radiation of different wavelengths, okay, so um, you can detect, you can measure as many as 70 elements simultaneously. Okay, here atomic emission enters the polychromator and is dispersed into its component wavelengths by the grating at the bottom here. Okay, this is a polychromator. One photomultiplier detector is required at the correct position for each element. Okay? You know the principle here. Okay? The emission wavelengths of each element is different. Okay, that's the principle, and the instrument has been more developed. Okay, this is a 2D display of atomic emission from ICP by charge injection device. Okay, this charge injection device is a two-dimensional. Okay, here this is a charge injection device, and the light, okay, light enters from this side, through this one, and then it is reflected here in this collimating mirror, and then reflected beam now goes to this uh, grating. It is called a shell grating. Okay, here. Okay, see, this is the with. Let me see. First, it enters into the prism. Okay, so vertical dispersion by the prism occurs. Okay, here by entering this prism. So it is depending on the wavelength. It is vertically, dispersed here. Okay, yeah, and then this vertically dispersed, the radiation now further dispersed by this SL grating here. This one, this SL grating makes horizontal dispersion, okay, by the grating here. This one vertically vertical dispersion first here, and then at this grating, and then horizontal dispersion, and then it's reflected by this mirror, and then it is detected by this two-dimensional charge injection device here. Okay, so this is the one example here. Okay, this is a two-dimensional, okay? And the y-axis is wavelengths, okay, in nanometers. Okay, and x-axis is gives us some different. Let me see, what the atomic mass. Okay, ion. It is ion detection. Depending on the isotopes, the mass is all different. Okay, it is displayed in this two-dimensional, the plane. Okay, yeah. So this is I think more sensitive. This is called constellation image, like stars in the sky, yeah? Inductively coupled plasma emission from 200 microgram ion seen by charge injection detector. Okay, and you know those bright spots above here, they are all argon. Yeah, it corresponds to argon. Yeah? But these all small, the spots, two-dimensional, those spots are corresponding to ion. Okay, yeah? For example, this one, yeah? This ion whose mass is 259.940, okay, and it is its wavelength is corresponding to here. Okay, you read the wavelength here, but here, this one, this blue color, this one, the mass is the same, yeah? But why? And then wavelength is the same, but why there are two spots? Because this is the number of order, diffraction order is different. This is 140 and this is 141. Okay, yeah, that's the difference